but exploding stars, okay, near the end of their life, which have collapsed and thrown off material. Here's such an object. Here's such an object, and it looks like two brains here that were emitted by this star. Same thing with this star. Here's a giant star formation region, a gas cloud whose length is a million light years. Excuse me, 1 light year, not a million. Hubble had a great view of the comet that struck Jupiter in 1990, what was it, summer of 1994, that left all these spots on the planet that were visible for several years. So there's a whole range. I mean, here's a star that's accreting material into a form of a disk, and we're seeing a star that's in the process of formation. So the fact is, there's all sorts of different science topics that Hubble has made really important contributions to. But what I want to focus on tonight are these guys here, galaxies, basically, which are the largest structures in the universe, or perhaps I should say clusters of galaxies. But I would go so far as to say, if you want to know what the largest structures are, self-contained, it is galaxies, typically, which contain anywhere from hundreds of billions to a few tens of billions of stars. So the fact is, if we believe in the Big Bang, and I'm going to come back to this, and what conditions were like there, how did we end up, which is, and I'll tell you, 14 billion years ago, but I'll mention how we get that number. How did we get to the time when we look out to objects in the sky near us now? Wrong button. We'll ignore that. How did we get those things? So there are three concepts I want to introduce. First, what's called look-back time. This is one of the great things about astronomy, right? Light doesn't propagate at infinite speed. Propagates 300,000 kilometers a second, which means that anytime you look out, you're looking back in time. I think all of you know this. When you look at the moon, we're seeing as it was 1 second ago. When we look at the sun, as it was 8 minutes ago. But the fact is, if we look out from Earth, which is in our home galaxy, the Milky Way, and a nearby galaxy, which is 1 million light years away, we're actually seeing the light from that galaxy as it was 1 million years ago. So of all the sciences, astronomy is the only one where you can actually see into the past. So as much as I think archaeology, paleontology are really cool sciences, they don't really look into the past. You see artifacts that require interpretation. In the case of astronomy, we can see the past. And the reason that's important is anytime you want to understand anything, whether we're talking people or whatever, it is always important to know what preceded the state that you were studying. That is, how did it evolve to get to what you are studying? And astronomy is the only science that actually enables us to look into the past so we can piece together how things evolved in time. So that's the most important concept, and we refer to that time as the look-back time. So when we look out to an object 1 million light years away, we're looking 1 million years into the past. So that's the first concept. Second concept, we live in an expanding universe. This was a concept that was basically determined by Edwin Hubble, which is why the telescope was named after him, American astronomer of 3/4 of a century ago, early in the 20th century, and Belgian astronomer Georges Lemaitre, who studied other galaxies, and they noticed that they were generally all moving away from us. That they had slightly different random motions, but the basic component of their motion was one in which they all seemed to be moving away. And so they realized, when they determined what the distances to these galaxies were, was that the universe is in a state of uniform expansion. And so this video illustrates it. And if I don't punch the wrong button here, I hope that we'll get, yeah, let's go back. So I've got to go down here. Here we go. The galaxies themselves are not expanding. They are gravitationally confined, but space between them, space itself is expanding. And it's expanding in a uniform manner. That is, it's sort of like raisin bread, right? It's got a lot of yeast in it. When you bake it, all of the little raisins move apart, and the further apart the raisins are, the faster their velocity. That is, the velocity they are expanding from any one raisin, any one point, or in this case, any one galaxy, is related to what their distance is. So the universe is in uniform expansion. Let me run this again. Although I probably don't really need to. The fact is, there's an important concept, I better not because I'll screw it up again. The fact is, if we are in a state of uniform expansion and you project backwards in time, what you conclude is that everything must have been confined to a much tighter configuration. And in fact, if it were exact, you would say that everything was confined to an extremely hot, dense region. Now, you might think, does this mean that there was some point that started all of this? I shouldn't get into this here because it'd take a separate lecture, but let me tell you that if the universe really is infinite, the fact that you can squeeze it down to an extremely small size still means that it is infinite. That is, there was no real point there. Another concept is, it's difficult for us with our finite minds to conceive of how can you take this whole gargantuan universe and pack all this material into something that's so tight. And the answer, we believe, is there was no matter at that time. Remember Einstein's equation, E equals mc squared, that there's an equivalence between energy and mass. It means that you can create mass out of energy, and you can create energy out of mass. We believe that the Big Bang was defined not by mass, but by energy. Now you might ask, interesting, so what produced that energy and what happened before it? Our answer, don't know. The reason we don't know is because science addresses those things about which we have facts. And I'm going to show you some facts that take us back very close to the Big Bang, but at this time, there is no information that we have been able to glean about the universe at the very instant of the Big Bang and whatever happened before it. So that's the realm of philosophy, religion, you know, whatever you like. So science, about which we have some facts that I'll show you, takes us back to the point very close to this point where we believe there was tremendous energy but no mass. Mass actually occurred, it was converted out of that energy billions of a second after the expansion. So, just FYI. So the point is, if we believe, as we do, the expansion, this uniform expansion of the universe, and the fact that we project back in time, well, what must the early universe have looked like? So, being scientists, we know what the physical laws are that we understand at this time. They're certainly incomplete, but in science, what you do is you take the knowledge that you have and you project consequences that predict something that you can confirm or deny. Now, we know that there are four basic forces that we're aware of in the universe: electromagnetic, two types of nuclear force, and gravity. And we believe that when we're dealing with large scales, there's electrical neutrality, magnetism's not important, nuclear forces are confined to extremely small distances, so the only force that should act in terms of our trying to understand the large scale properties of the universe is gravity. And gravity is an attractive force. So remember that. if we're trying to project what the universe is like starting here, okay, present time. So we hypothesize, we project, projecting backwards from the present time where we look out and we see stars and galaxies that look sort of like you see on the right there. What were things like way back here in time? The laws of thermodynamics tell us that anytime you take material and you compress it, it's hotter. You expand it, it gets colder. And so we believe that in order to understand the early phases of the universe, from the fact that it is now in uniform expansion, is at some point it was really hot and really dense. So we believe at some point as we approach the Big Bang, there was probably what we believe to be a hot gaseous plasma, a hot fog. Now anytime you heat something, it radiates. And so here's something that we might be able to observe, this hot fog. And it would confirm then our notion that there was a Big Bang. Did it happen? Yes, actually, it resulted in a Nobel Prize. So one of the really interesting early NASA missions called COBE, Cosmic Background Explorer, in the 70s, basically looked for this radiation that we thought might exist that we could see from the hot fog in the early universe. So what they did was they sent something up into space where you didn't have the Earth's atmosphere limiting, giving you a background that would confuse things. And with a very wide field, looked between the stars, between the